In this last segment, we're going to talk about random walks on undirected graphs. And to motivate this problem, we're going to talk about the ST connectivity problem. And in this problem, consider a very large graph G. It's undirected and unweighted. This graph has n vertices and n is large. So it's a classic big data problem. It also has a lot of interesting implications elsewhere, but let's focus on the big data aspect. You're given a source vertex S and also a sink vertex T. Okay. Now, we don't know if this graph is connected, and in particular, we don't know whether there is a path between S and T, and that's the question we're interested in. We want to know if there is a path between S and T. This is not very difficult. We've all been through some form of algorithms course, and you've studied BFS, DFS, and so it's easy to solve. But the big data context comes from the fact that you're not allowed to use a lot of space. Now, if you were to use BFS, you will need to have a queue of up to theta of n size. And similarly, even if it's DFS, you will need to have a stack of up to theta of n size. And either of these is unacceptable. And therefore, we need a solution that takes very little space. And as I alluded to, this problem has very interesting complexity theory implications. In particular, the question of whether symmetric non-deterministic log space computation equals deterministic log space computation. This was a big open question that got resolved in the mid 2000s thanks to Omer Reingold. So this is a very famous paper, but this talks about a deterministic solution, and it's not a very practical solution to be implemented in real-world applications. And so we are more interested in a solution that is easy to implement and easy to analyze and easy to appreciate. So we are interested in a random walk space solution. And what is a random walk? At each time step, think of a particle or a token that's at some vertex. At each time step, this token takes a random walk step. What that means is from its current location, let's call that V, it chooses one of the dV neighbors of V uniformly at random and moves to that neighbor. And each step is independent of previous steps that it took. So it only depends on where its current location is, and that will and from there one of the neighbors is chosen uniformly at random. And so what we do is simple. We start a random walk from S, and we allow it to walk for some number of steps, and hope that it will reach T. So, of course, if it reaches T, then that means S and T are connected. But if it doesn't reach T, well, does that mean that S and T are not connected? It might just be the case that, well, this random walk just somehow avoided T. And so we need to be concerned about that, and we need to understand whether that will happen. And from your previous lectures where we talked about finite irreducible and ergodic Markov chains, you probably have some intuition that it won't miss some part of the maze. But the problem is, how long does it take to actually cover the entire maze? That's important, because that tells you that if you walk that long and still don't see T, then S and T are probably not connected. So that's the intuition that we're going to work with. Okay? So we want to find that amount of time for which that random walk should walk before we can safely conclude whether S and T are connected or not. And as it turns out, that that number of steps is 4mn cubed in order to get a confidence of 1 minus 2 raised to the minus m. But why is that? Well, that's what we are going to delve into in this segment. And just to, in case you missed this point, notice that the position of the token it can be thought of as a Markov chain. So the position is a vertex. So the Markov chain has n states, basically each state corresponding to some vertex in which that token is present. Okay, and let's start delving into this notion of random walks. Let's look at the first lemma here. A random walk on an undirected connected graph G is aperiodic if and only if G is not bipartite. So, in other words, the graphs that are not bipartite are more interesting, and if you care for aperiodicity. Eh, let's see how this lemma can be proved. Okay, so this is an if and only if statement. So the proof has to go in two directions. The first direction that we're going to prove is aperiodic implies not bipartite. Or equivalently, let's look at the contrapositive. Bipartite implies periodic. Well, this is very easy to see because if it is bipartite, then what happens is there are two parts to the graph, and the random walk will stay at one side during odd times and the other side during even times. So it's quite easy to see that a bipartite graph is going to a random walk on a bipartite graph is going to be periodic. So the forward direction is proved that way. What about the reverse direction? Well, this one we need to show that a graph that is not bipartite, a random walk on that such a graph, will be aperiodic. Okay, an odd a graph that is not bipartite is must have an odd cycle. Okay, and if there is an odd cycle, what that means is that you can always go from one vertex. You can find a way. Assuming the graph is connected, you can find a way to take a walk from a vertex and return to it after an odd number of steps. And of course, you can also do even number of steps. You can just go back and forth between the node and its neighbor. So combining these two, you can mix and match them and create walks of any length beyond a certain threshold. And this is the crucial idea by which we can establish that with some non-zero probability, you can actually go from any vertex to another vertex at a variety of different time steps. In other words, such a random walk will be aperiodic. Okay, so that's the intuition. This is not a complete proof, but I want to leave you with an intuition for why this statement holds. Okay. So for the rest of this segment, let's keep things interesting. We've been interested primarily in aperiodic Markov chains. So we're going to assume that G is not bipartite. Okay, so this means that a random walk on such a graph is going to be aperiodic. Now let's look at the stationary distribution of a random walk on a non-bipartite connected graph. The claim is that the component associated with a vertex V is given by dV over 2 times the number of edges. Okay, why is this? First of all, we need to show that this stationary this is first of all a distribution. This vector of numbers, quantities, is first of all a distribution. We need to show that. Well, these quantities are going to be between 0 and 1. That's clear. What we need to show is that they add up to a 1. Okay. Well, let's see how that's going to work. Now, if you sum up the degrees, that's going to equal 2 times the number of edges. Okay, and so if you rearrange, you're going to get dv over 2e summed over all vertices, going to add up to 1. Great. So, well, but dv over 2e is nothing but the component associated with v, and so this is exactly what we want. So we know that uh, this vector of numbers is a probability distribution. Now we need to show that this equation holds. This probability distribution vector times the transition matrix will give you back the probability distribution vector. That's what needs to be shown. Okay, so let's look at this equation from the perspective of a single vertex. So that's pi v. When you apply this matrix, when you multiply it by this matrix, what does that mean? Well, the pi v um, is, well, let's look at the vertex v. Its neighborhood, these are its neighboring vertices, and that's denoted by nv. Okay, so in order to get this component pi v, what we have to do is sum over all the neighbors of v, okay, and take their corresponding vector components times the probability with which the random walk a random walk token from one of these neighbors, say u, will move to v, and that's this quantity 1 by du. Why is that? Well, if you look at the vertex u, there are du neighbors, and each one of them is chosen equally likely. So the probability that a random walk token that's at u will take this edge and come to v is 1 over du. So pi v is summation over all the neighbors u, the stationary distribution component corresponding to u, times the probability with which the token will move from u to v. Okay, that's essentially what we do over here. Okay, and canceling these two du's, we will get 1 over 2 times the cardinality of the edge set. But then we're summing over the neighborhood of u, and so we get dv over 2 times the cardinality of e. Okay, so this completes the proof of our claim that the vector formed by these components is the stationary distribution of this random walk. And of course, we can immediately conclude that the expected time for a random walk to leave v and return back to v is the reciprocal of pi v, which is 2e over dv. Okay. Let's look at a slightly more general HVU. So let's assume that let's focus on an edge in the graph. Okay. Now the expected time to go from v to u is at most 2 times the cardinality of e. Of course, if you're lucky, you will go in one step. But what this claims is that even if you're unlucky, the expected time to go from a vertex v to its neighbor u is at most 2 times e. Okay, and here's how the proof goes. So let's look at HUU. We already know that HUU is 2e over du, and this is what we got over here. Okay, but there's also another way to look at this. Okay, so from u, with probability 1 over du, we will go to a neighbor w. And from that w, we will eventually make our way back to u, and that's hwu. But then that's just the option of going to w. Using the law of total probability, we can sum this up over all neighbors of u, and so as a result, we get this quantity. So it's a summation over all the neighbors w. You go to this one corresponds to the one step that we take to go to w, and this hwu is the expected number of steps that we take from w to u, and this option is exercised with probability 1 over du, and this is just one of many options, in particular one of nu number of options. This is the number of neighbors of u, and applying the law of total probability, we get this expression for huu. Okay, so this is two ways of computing huu, and so the du's get cancelled. We'll get 2e equals summation w belonging to the neighborhood of u 1 plus hwu. And of course, one of these w's is the v, the neighbor v that we're interested in. So clearly, looking at this summation, the expected time to go from v to u must be in fact strictly less than 2 times the number of edges. Okay, so why did we even look at this? This is actually an interesting consequence. There's an interesting notion called the cover time. Well, you may start to realize why we're going to talk about the cover time, because this will have a bearing on the problem that we started out with. Well, what's the cover time? It's the expected time by which a random walk has visited every node in the graph, regardless of its starting point. So it's the worst case time, expected time, for a random walk to have explored the entire graph. And of course, we're talking about a connected non-bipartite graph. Okay. More formally, it's the maximum over all vertices in the graph, the expected time for a random walk starting at v and visiting all the nodes. Okay. The cover time of a graph G equals v comma e is at most 4 times the number of vertices times the number of edges. This is true for any graph. For special graphs, we have better bounds on the cover time, but this is true for any connected non-bipartite graph. Okay. So why is this the case? Well, consider a spanning tree of G. Okay. Now, if you consider the edges in DFS traversal order, and now you have to consider it both directions. So each edge will be traversed in 2 directions. That ordering will have at most 2 times the number of edges minus 1 number of vertices v minus 1 number of edges. Okay, why? Because the minimum spanning tree has n minus 1 edges, and each of those edges will be traversed at most twice. Okay, so these are all edges in the graph. So the expected time to go from one end to the other is at most 2e. So this naturally leads us to the conclusion that the cover time is at most 4 times v times e. Okay. So back to ST connectivity. We know the cover time is at less than 4 VE. Okay, and that's at most 2n cubed, because the cardinality of the edge set is n squared, is less than n squared by 2. Okay. Well, let's use r, the random variable r, to denote the time to reach t starting from s. Remember the algorithm? We start from s. We just started a random walk, and we allowed this random walk to walk. And r is the now let's assume that the graph is connected for the purpose of analysis. Um, r is a random variable that denotes the time to reach t from s by this random walk. And from Markov's inequality, well, we know that the expected expectation of r is 2n cubed. Okay. From Markov's inequality, what is the probability that r exceeds 4n cubed? Well, that's at most a half. Okay. So if we run it 4m n cubed number of times, and here m is just a parameter, not to be confused with the number of edges, because m is often used to denote the number of edges. Here is just a parameter. If what's the probability that r exceeds 4m n cubed? Well, it's at most 2 raised to the minus m. So, and if you make m, for example, something like log n, this quantity will become 1 by n. So so when s and t are connected, the algorithm after these 4mn cubed number of steps will conclude that s and t are connected with high probability. On the other hand, if it is if after 4mn cubed number of steps you don't reach t, then you conclude that the graph is, I mean, the S and T are not connected. And what's the probability with which you will be wrong? Well, that's a small, at most 2 raised to the minus m. So that brings us to the end of this series of segments. Thank you.